Good morning. Today we will discuss about plane transmission grating or diffraction grating. So grating is an arrangement of large number of slits on a plain glass sheet, glass-like sheet. Okay. So it is constructed using diamond point. So using this diamond point, we are drawing large number of lines on the surfaces of a glass-like material, and the lines on this plate will represent will be opaque to the light, and the spaces between these lines will be transparent to the light. So this will constitute a grating. So this is a grating. It is an arrangement of large number of narrow rectangular slits. Okay. So usually when a white light is incident on the grating, it is transmitted to this slit and is obstructed by these opaque portions. So this usage of this transmission grating usually is in the range of 5,000 to for the visible region, and contains nearly 5,000 to 7,000 lines per centimeter. So you imagine the number of slits per centimeter of a grating, that is 5,000 to 7,000 lines per centimeter, means that much number of slits are parallel slits are arranged in a grating. So this is a grating. Okay, so how this grating is working, or how it can be used in order to produce intensity pattern on the okay. In order to explain this, let's look at this figure. This figure, this represents the grating in which this A, B, C, D, E, F represents the slits. We have already said that grating is an arrangement of okay. So this is the grating, and we are placing the source of light here, and which is allowed to follow normally on this slits. So this AB represents A, B, C, D, E, F, etc. represents the slits, and B, C, D, E, F, I, etc. represents the opaque regions. Okay. AB is of width A and BC of width B. So A plus B represents from the point A to point C. So the A point from A is corresponding to a point from C. Similarly, a point from B corresponding to a point from D. Okay. So this is the situation. Now what we are observing is we are looking at the rays coming parallel or coming in the same direction from this slits. That is a plane wavefront is incident on this slits. So from this plane wavefront, secondary waves are produced, and this can travel through the slit along any direction towards this region. Okay, so first we are considering the light coming in the same direction, and which we are focusing using a lens on this screen. So this will focus on this point, that is at the focal point of this lens. Okay, and we can check whether this point is maxima or minimum. This point will be a maximum because these rays traveling in this straight line or straight path will not have any path difference between them, so they will constructively interfere here. So we will get a central maximum point here. Okay, so we will get a central maximum point at the point P. Now we can get another different ordered maxima or maximas on either sides of this P according to the condition of the path difference of the light reaching here. So the light can travel along this direction, or from this direction, any direction. The light can travel from any travel in any direction through this slit. So we have seen only the light traveling in this direction here, which is constructively interfere here and produce maximum central bright point. Now we can check another light rays coming through the slits which are traveling in this direction. For this, let's look at the second figure. So here is the second figure. In this, we are considering the first two lights coming from the first two slits which are traveling in this direction, which making an angle theta with this direction of this straight direction. Okay, so at this point, what will be the brightness, whether it is maxima or minima? We can check by seeing the path difference between the lights reaching here. So for this, we are considering the light coming from the point A and coming from the point, this point. Actually, this line is at the end point of this, so this will represent the corresponding point. So corresponding to this point, this line represents point from here. So we are considering here the corresponding points. Okay, or if we are considering a light rays coming from the middle of this AB, then we have to consider another lines coming from the middle of this CD, that which is calling as corresponding points. Okay, so corresponding light rays are considering here, and the path difference between these two rays will be this much, that is CD. Beyond this CD, the path difference is 0, reaching at this point. So we have to find out the path difference as in the previous classes. So CD from this angle CAD, sin theta is equal to CD by AC, that is opposite side by hypotenuse. From this, CD is equal to AC sin theta, where AC is the AB plus BC, AB plus BC, where AB is A and BC is B. So we will get the path difference as A plus B sin theta. So this point Q will be of maximum or minimum intensity according to the condition of whether this path difference is corresponding to n lambda or vice versa. Okay. So if A plus B sin theta is equal to n lambda or integral multiple of lambda, then we will get maximum intensity there. Okay. Usually the point Q will be of maximum intensity if this path difference is integral multiple of lambda. Okay. Now thus all the secondary wavelets starting from different corresponding points of the neighboring slits reinforce one another and produce principal maxima at Q. By this condition, we can say that all the light reaching there will be of maxima intensity if it satisfies this condition. Then we can write in general A plus B sin theta n s n lambda for nth order diffraction. For n varying from 1, 2, 3, etc., we will get first order, second order, third order principal maximas. Okay, so the central point is called central maxima, and this point represents the first principal maxima corresponding to n is equal to 1, and another point we will get beyond Q second order principal maxima, etc. And similarly to the lower side of P, we will get first order maxima, second order maxima corresponding to the value of n is equal to 1, 2, 3, etc. And this equation is known as the grating equation. This is grating equation. And if there are n lines per unit length of grating, I have drawn here a picture in order to understand you this meaning. That is, if this is represents a unit length, and if there is n number of lines, then there are n number of slits also. So A plus B will contribute a slit plus opaque region. So A plus B into n will represents the total length, which is unity, which is equal to 1. Okay, so we can write n into A plus B is equal to 1. From this, A plus B is equal to 1 by n. So we can substitute this value here. So that 1 by n is sin theta n is equal to n lambda. From this, sin theta n is equal to n lambda. So this is the general grating equation, where capital N is the total number of slits in the grating, small n is the order of diffraction, and lambda is the wavelength of light used, and sin theta is the angle of diffraction. This represents the diffraction grating. This is represents the grating equation. So this is the theory. So what we'll get on the screen is, if you are using a slit, if you are using the grating, which is an arrangement of large number of rectangular slits, if you are using a grating and a source of light, here we will get a central bright point at the center, and first order maxima, second order maxima on either sides of the central bright point. Okay, so this is about grating, theory of grating. And if you are using a white light to illuminate the grating, we will get colored spectrum on either sides of the central maximum point, because the white light is composed of colors varying from, or wavelength varying from 400 to 700 nanometer. So all the light will constructively interfere at the central point, because the path difference between the light reaching the central point will be 0. So they will constructively interfere, and we will get white light at the central point. And on either sides of this white light, that is central maximum, central bright point, we will get colored spectrum. Because from this grating equation we can see sin theta is equal to capital N into lambda, where theta is the angle of diffraction, which is different for different wavelength for a given order. That is, for suppose n is equal to 1, then the theta will be one value for lambda is equal to blue color, and theta will be another value for blue wavelength is equal to red, or wavelength is equal to green, violet, etc. So for different color, the diffraction angle will be different for a particular value of n. That means we will get different order colored spectrum on either sides of the central maximum point according to this different diffraction angle. So if this angle of diffraction is different, then we will get different colors on this spectrum, and this order will be changing according to the value of n. So we will get different order colored spectrum on either sides of the central white point. Okay, so in addition to this, so if you draw the intensity pattern of this diffraction grating, we will get a graph like this. So this is intensity. So this at the central point we will get maximum intensity. This is a central maximum intensity point, and these are 1, 2 marked on either sides represents the principal maximas. This is the first order principal maxima, second order principal maxima, and similarly on either sides of the central bright point. And in between these principal maximas, you can see another maximas and minimas. These are called secondary maximas and secondary minimas. So how these secondary maximas and minimas are produced, we can check. Okay, so the principal maximas are formed for any wavelength for the orders of n is equal to 1, 2, 3, etc. for respective angles of theta 1, theta 2, theta 3, etc. that we have seen. So in between this we are getting the secondary maximas and minima. For a wavelength lambda, let the first order principal maximum be formed for an angle of diffraction theta 1. So let the first order principal maxima is formed for an angle of theta 1, and the second principal maxima is formed for an angle theta 2. Okay, so in between we are considering this theta is increased by a a small value d theta, but it is not reaching theta 2. That is, we are considering an angle of diffraction in between this theta 1 and theta 2. That is theta which is greater than theta 1 and less than theta 2, and which is represented by a increase from the value theta 1 by a quantity d theta. So that is represented by theta 1 plus d theta, which is as theta prime, which is less than theta 2. Then the path difference between the secondary wavelets from the ends of the single slit of width f a can be represented like so. In the previous pictures we have considering the light coming from the corresponding points of two slits, that is from the point A and from the point C, or from the point B and D. So here we are considering the single slit, that is light coming from the ends of a single slit. So the path difference between these lights coming from the endpoints of a single slit is represented by Bn prime, where Bn prime will obtain as a sin theta, as the similar procedure we have done in the previous figure. So the path difference between the endpoints of the light of a single slit is a sin theta. So this light, if these lights combine at any point, then that point will be maxima or minima according to the condition a sin theta prime is equal to m lambda, where m varying from 1 to 3 or m varying from 3 by 2, 5 by 2, 7 by 2, etc. That is, we will get secondary minima point for m is equal to 1 to 3 values, and secondary maxima for values m is equal to 3 by 2, 5 by 2, 7 by 2, etc. That is, this is the condition where sin theta is equal to an integral multiple of lambda, or it is an odd integral multiple of lambda. This is an odd integral multiple of lambda by 2. Okay, so according to that we will get maxima or minima on the screen. That represents the secondary maximas and minimas on the screen. Okay, that's how we are getting the secondary maximas and minimas. So this represents the superposition of lights coming from a single slits. Okay, so this represents the superposition of lights coming from different slits, and this maxima and minimum intensity is according to the condition of path difference, whether it is equal to lambda or integral multiple of lambda or odd integral multiple of lambda by 2. Let n be the number of slits in the grating, that is, let us say n is equal to 5, capital N. So we will get a pattern like this, that is 5 maximas, 1, 2, 3, 4, 5 maximas, and the number of secondary maximas and minimas are will obtained as n minus 1 and n minus 2, that is n minus 1 secondary minimas and n minus 2 secondary maximas. We can see from secondary minima, that is 1, 2, 3, 4, n minus 1 secondary, here also 1, 2, 3, 4, n is equal to 5 means 5 minus 1, 4, and n minus 2 secondary means 1, 2, 3, 1, 2, 3, etc. Okay, so we can find out the number of secondary maximas and minimas by knowing the number of capital N. Okay, so this is about diffraction grating. Thank you.